Hello and welcome back to this channel once again. In today's lesson, we are going to talk about parallel and series capacitors. Now, from the previous discussions on parallel and series combination of resistive circuits, we got to realize how important and powerful this tool was in reducing a complex circuit into a more simpler form for easy analysis. Now, in today's lesson, we are basically going to extend this same concept to capacitors, where we are going to learn how to find the equivalent capacitance in series and in parallel. Now, if you are new here, make sure you subscribe to this channel, like the video, and share the video to all your friends. Now, let's get into today's lesson. Let's start off with capacitors in parallel. Now, suppose that we have two capacitors, C1 and C2, connected in parallel, and then we have a source voltage V connected across each of the two capacitors. Now let the charge on the first capacitor C1 be Q1 and the charge on the second capacitor C2 also be Q2. Now, from the formula, which is given by Q is equal to C times V, and then having in mind that for capacitors connected in parallel, we have the same source voltage V connected across each of them. So what this literally means is that the voltage across C1 is V and the voltage across C2 is also V. So from this formula, charge is equal to capacitance times voltage, and then having in mind that we have the same source voltage V connected across each of the two capacitors, then it means that the charge on the first capacitor C1 is equal to C1 times V, and the charge on the second capacitor Q2 is said to be C2 times V. Notice that we have the same source voltage applied across each of the two capacitors. Now at this point, if we want to replace C1 and then C2 by a single capacitor, then what this primarily means is that we want to find the equivalent capacitance. Now in this case, you realize that the total charge produces the same source voltage. So in this case, we have the total charge to be Q1 and Q2. So that's we have Q1 plus Q2 being the total charge, which is going to produce the same source voltage, so that we have C equivalent times V. So Q1 plus Q2 is equal to C equivalent times V. Now, if we want to replace Q1 and Q2 by C1 V and then C2 V, then it means that we are going to have C1 V plus C2 V, and that is equal to C equivalent V. Now at this point, you realize that V is common to each of the terms, so we can cancel out V so that we have C1 plus C2 equals C equivalent. Now let's call this equation 1. Now what this primarily means is that for capacitors in parallel, the equivalent capacitance is equal to the arithmetic sum of the individual capacitors involved. Now in addition, since we have the same source voltage expressed across each of the two capacitors, it means that the source voltage V is equal to the voltage applied across C1 and the voltage applied across C2. Again, the charge on each capacitor may be different. That is, the charge on C1, which is Q1, may not necessarily be equal to the charge on C2, which is Q2. Okay, the charge on C1 and then C2 may be different. However, the total charge Q is said to be equal to Q1 plus Q2. So basically, these are some of the formulas we are going to use to either find the equivalent capacitance, the voltage across each of the two capacitors, as well as the charge on each of the two capacitors, considering parallel combination of capacitors. Now let's move on to capacitors in series. Now for capacitors in series, assuming that we have two capacitors C1 and then C2 which are connected in series, and then we have a source voltage V connected across them. Now in this case, the charge on each of the capacitors is going to be the same. The charge on each of the capacitors is going to be the same, which means that the total charge in the circuit Q is equal to the charge on C1, which is equal to the charge on C2. So Q is equal to Q1 is equal to Q2. Now let V1 be the voltage drop across C1, and then V2 also be the voltage drop across C2. Now what this literally means is that the sum of the voltages dropped across the capacitors is equal to the source voltage. Now from the formula, that is Q is equal to C times V. Now from this formula, we can say that Q, which is the total charge, is equal to C1 times V1, and that is also equal to C2 times V2. That is from this concept that the total charge is equal to the charge on C1, and that is also equal to the charge on C2. From this, we can have these two equations, that is Q is equal to C1 V1 and Q is equal to C2 V2. Now also from these equations, we can try to make the voltages the subject. So we can try to make V1 and then V2 the subject. So making V1 the subject, we are going to have V1 equals Q divided by C1, and then making V2 the subject, we are going to obtain Q divided by C2. So in that regard, having in mind that the source voltage is equal to the sum of the voltages dropped across the capacitors, so that is V is equal to V1 plus V2. From this equation, we have V to be equal to the total charge Q over the equivalent capacitance. Okay, we are going to have V to be equal to, that is the total voltage, or the source voltage is equal to the total charge divided by the equivalent capacitance. Okay, so that is that, and this is here is the same thing here, and this is equal to V1. V1 is Q over C1, and then plus V2, which is Q over C2. Now from here, we can cancel out Q because Q is common to each of the terms, so that we can have 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Let's call this equation 2. And what this primarily means is that for capacitors in series, the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitors. Now in addition, since the same charge is stored on each of the capacitors, then we say that Q, which is the total charge in the circuit, is equal to Q1, and that is also equal to Q2, while the voltage across each of the capacitors may be different. And since we know that V, which is the source voltage, is equal to the sum of the voltages dropped across the capacitors. Now, how do we find the voltage drop across C1 and the voltage drop across C2? So to do that, we say that V1 is said to be the value of the second capacitor divided by the sum of the two capacitors times the source voltage, and then also V2 is also giving us the value of the first capacitor divided by the sum of the two capacitors times the source voltage. So basically this is how to find V1 and then V2. Now, having gotten this, let's move on as we solve a couple of examples. So for the first question, that is question 1, 3 capacitors have capacitances 20, 40, and 80 microfarads. Now find the total capacitance when they are connected in A, parallel, and then in B, series. Now let's solve this together. So from the question, we are given 3 capacitors. We have the first one, C1, that is equal to 20 microfarads. We have C2, 40 microfarads, and then we have C3, that is 80 microfarads. And then we want to find the equivalent capacitance when they are connected in parallel and in series. So first of all, for capacitors connected in parallel, we know that the equivalent capacitance is equal to the algebraic sum of the individual capacitors. So here we have 3 of them, so that is C1 plus C2 plus C3. Now let's input the various capacitor values. So here we have 20 plus 40 plus 80. Now 20 plus 80, that is 100, plus 40, we have 140. So that's going to be 140 microfarads. Okay, 140 microfarads. That is the equivalent capacitance for the parallel combination. Now let's move on to B. For B, we want to find the equivalent capacitance in series. Now we said that for capacitors in series, the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitors. Therefore, we have this to be the formula because we have 3 capacitors. Therefore, we can say that 1 over C equivalent is equal to 1 over 20 plus 1 over 40 plus 1 over 80. Now, if you add these 3 fractions, then you are going to obtain 7 over 80. And then we can have C equivalent, that is the reciprocal of this, to be 80 over 7, which is equal to 11.4286 microfarads. Now, assuming that we want to leave our answer to 2 decimal places, then we are going to have C equivalent to be equal to 11.43 microfarads. Now, this is the equivalent capacitance combination in series. Now, let's move on to the second question. So for the second question, if 2 capacitors of capacitances 6 microfarads and 10 microfarads respectively are connected in series across a 100 volt supply, find A, the voltage across each capacitor, and then B, the charge on each capacitor. So how do we solve this? So first of all, we have 2 capacitors, C1 and C2. We have C1 6 microfarads, we have C2 10 microfarads, and then we have source voltage 100 volts. Now we are being told that the 2 capacitors are connected in series. So we have the voltage source, that is 100 volts, and then we have C1 and C2 connected in series. So let's say we have this to be the connection. This is C1 and then this is C2. Okay, and then for capacitors connected in series, we have the same charge, okay, on each of the two capacitors. Now, we want to find the voltage across each of the two capacitors. So to find the voltage across each of the two capacitors, then it means that we want to find V1 and then V2. Okay, so we said that to find V1 is equal to the value of the other capacitor, which is C2, divided by the sum of the two capacitors times the source voltage, which is V, in this case 100. Therefore, we are going to have C2, which is 10 microfarads, divided by C1 plus C2, and then times 100. Now, 10 divided by 16 times 100 is equal to 62.5. So that is 62.5 volts for V1. And then also for V2, that is equal to C1 divided by C1 plus C2 times 100, that is equal to 6 divided by 6 plus 10 times 100, and that is also giving us 37.5 volts. So literally when you add V1 and V2, it should be equal to 100 volts. So these are the voltages across C1 and then C2 respectively. Now let's move on to B, where we want to find the charge on each capacitor. For capacitors in series, we have the same charge on each of them. So this literally means that we can have, or let's say we have Q is equal to C1 V1, and that is also equal to C2 V2. So we can use any of them. So assuming that we use C1 V1, then we can say that, let's say we are using C1 V1. So for Q equals C1 V1, then that is equal to, we have C1 to be 6 microfarads. So let's say 6 microfarads, okay, times V1, which is 62.5 volts. So 62.5 volts, okay. Now this is equal to, here we have 6 times 62.5, and that is giving us 375, and then we have micro, so micro coulomb, so 375 microcoulomb. That is the charge stored on each capacitor. Now let's move on to the third question. So for question 3, two capacitors 5 microfarads and 20 microfarads are connected in parallel across a 200 volt supply. Find A, the charge on each capacitor, and then B, the total charge. So here we have two capacitors in parallel. So we have this to be the source voltage 200 volts, and then two capacitors connected in parallel. So let's say this is C1, and then this is C2. So C1 and then C2. Great. Now we want to find A, the charge on each capacitor. So let the charge on C1 be Q1 and the charge on C2 also be Q2. Now for capacitors in parallel, the charge on each of the capacitor may be different, okay. Now we also know that for capacitors in parallel, we have the same source voltage applied across each of them. So the voltage across C1 is the same voltage across C2. Therefore we say that V is equal to V1, that is equal to V2, and that is equal to 200 volts. Now to find the charge on C1 and C2, for C1 we have the equation that is given by charge is equal to capacitance times voltage. Therefore we say that Q1 is equal to C1 times V, and Q2 is also equal to C2 times V. So let's find Q1. Q1 is equal to, we have C1, which is 5 microfarads, times V, which is 200 volts, and this is equal to, now 5 times 200 is 1000, so we have 1000 microcoulomb, which is Q1, and also for Q2 we have this to be equal to, that is for Q2 we have 20 microfarads times 200 volts, and that is also equal to 20 times 200, that is 4000 microcoulomb, that is Q2. So this is the charge on C1, and this is the charge on C2. Now we want to find the total charge. So the total charge Q is equal to Q1 plus Q2, and that is equal to 1000 plus 4000, which is equal to 5000 microcoulomb. So that is the total charge in the circuit.